In this lecture we'll look at an extremely important area of growth, and that is quality of service. At the present time we're moving from our plain old telephone system which used switched technology and private branch exchanges towards using the internet and IP networks to carry voice traffic. The internet, though, has been built to carry data so that factors such as latency and jitter are less important. The key focus for the internet has been on reliability and reduced error rates. If we add voice has a different characteristic and typically does not require a great deal of bandwidth for each connection, but it can suffer in delays and also in jitter. Data also tends to be fairly bursty in that data can hog a network connection for a length of time which can swamp voice traffic. Along with this, data can be split into business critical data and normal data. What we want to make sure is that business critical data is not swamped by normal data. So quality of service is all about trying to optimize the transmission on the network, especially focused on key objectives. For voice, we start off with the voice signal, which might look something like this. We typically see harmonics in speech. And then what we do is that we sample it a number of times per second. It was Nyquist that showed that the sampling rate should be twice the highest frequency of the signal. As in normal telephone, the highest frequency is 4000 Hz or 4 kHz. The sampling rate is typically 8000 times per second, or once every 125 microseconds. So we end up with a number of samples, which gives the height of the wave. Then we feed this into a digital analog to digital converter to convert it into a binary format. This is typically a 12-bit converter. After this, we compress the output, typically to give a bias towards the lower signals as opposed to the stronger signals. And we convert from 12 bits into 8 bits using using something like mu law compression or A law. At the output here for every sample we have 8 bits. This is then serialized into a bit stream. If we have 8000 samples per second and there are 8 bits per sample, then the base rate is 64 kilobits per second. Previous voice transmissions have been built around ISDN, E1 and T1. ISDN gives us our base rate times 2, where we can have two 64 kilobits per second data streams. Both or one of them could be voice or both can be data. There is also a 16 kilobits per second signaling rate. This gives us a base of 128 kilobits per second. Overall, the transmission rate for ISDN is 160 kilobits per second. In the US, the T1 PRI, primary rate ISDN stream, takes 24 of these 64 kilobit per second streams into a TDM stream and then adds a 64 kilobits per second signaling stream to give 1.544 megabits per second. European type systems are typically built around an E1 PRI, primary rate ISDN, which takes 30 of these streams, adds on a 64 kilobits per second stream to give us 2.048 megabits per second. This is the existing way that many telephone networks transmit their voice signals. These are then multiplexed up until we get extremely high rates. The objective of voice is to try and integrate voice, video and data into an IP network. The key focus of this is on the management of the network, to have high availability. We don't want our telephone network to fail at any time. Security is obviously a key factor, especially for things like playback or to be able to interrupt conversations, and for quality of service. As we'll find, the key metrics involved in voice are to define the necessary bandwidth, to define an acceptable delay or latency, define an acceptable amount of jitter, and to define an acceptable amount of loss. It is the AVVID architecture which tries to implement this. So the key factors for voice is that it requires a constant need for bandwidth. The signals themselves typically are constant, not a great deal of bandwidth for every signal, but there is a constant need for it. What we want to stop is data coming along and bursting onto the network while we are transmitting this voice data. It is also delay sensitive, and that matters how long it takes each of the intermediate devices to process the voice data. It is jitter sensitive, but it is relatively error insensitive. The odd error in a data packet doesn't really matter that much, because the voice data can be easily filtered to produce the required output. Data, on the other hand, tends to be fairly bursty. It isn't constant, and it tends to go from low requirements to high requirements. It doesn't matter too much how long it takes. It doesn't matter too much the variation between the time it takes to transmit a signal, but it is error sensitive. The key factors that we'll see in quality service are to classify the traffic, to try and shape it in some way, to define prioritized queues for voice and data, to try and avoid congestion before it happens, and to try and compress different traffic flows. So what is the basic calculation for voice? Basically, we have, if we're transmitting in an Ethernet frame, we have a start and an end of our frame. After this, we might have our IP header, and then voice packets are typically transmitted within UDP rather than TCP to give them a low overhead. We have our UDP header. After this, we have a protocol such as RTP, and then we have the basic voice payload. The simplest one here is an 8 kilobits per second compressed stream, which only requires 40 bytes for our voice payload. A 32 kilobits per second stream gives us higher quality. That gives us 120 bytes, and then a pure 64 kilobits per second stream gives us 160 bytes. If we take this as an example of a pure stream, it gives us our worst case. If we add up all the numbers, each data frame that's sent is 218 bytes long, so it isn't a long data frame. Typically, we create 50 packets per second for our sampling, so then the total amount that we have is the number of bytes times bits times the packets per second, so we have 87.2 kilobits per second. That is the base rate. So we can actually estimate the amount of bandwidth used by the voice by taking this rate and multiplying it up. Obviously, if we use different payloads, we can reduce this amount, but this gives us our baseline. A key factor in a voice over IP network is to provide electrical power to the phone, as we typically do not want to have an external power supply for it. So it is up to the Ethernet connection to provide the power. So for this, we must provide power over Ethernet. We can do this in several ways, such as an in-power Ethernet module that fits into a switch, and each of these ports gives the Ethernet connection along with the electrical power for the phone. We can also buy a switch which has integral power. This is the 3524 power switch. Each of these ports has electrical power, and we can also do it from the patch panel when an electrical supply is supplied to the panel and the power is added to each of the Ethernet connections. For good design practices at layer 2, it is a good practice to create separate VLANs for data and voice. The good thing about this is they are kept within the same broadcast domain and can be switched. STP features should include port fast, uplink port fast and root guard to protect for STP attacks, and we should use some form of tagging in order to define the quality of service. At layer 3, it is a good idea to use an event-driven routing protocol such as OSPF or EIGRP. There should be passive interfaces at the access layer when we connect, so that routing tables are not broadcast into a network where there is access. And HSRP or GLBP are used for gateway redundancy, so that nodes can find alternative gateways. Typically, what their prioritization is that voice and video are given the highest, transactional applications such as business critical applications are second, and data transfer has the lowest priority. Okay, so what are the key metrics that we use for quality service? These are delay, jitter and packet loss. With delay, the amount of time it takes to be transmitted over the system actually matters. In this case, we have created a delay of 60 milliseconds. If this delay is too great, then the connection can actually drop. Jitter depends on the variation between transmitted signals. In this case, the jitter must be less than 60 milliseconds. The delay, a delay should be less than 60, and the jitter should be less than 20 milliseconds. And then we can have packet loss. In this case, this packet has been lost, and this one. There is a requirement for good error, a reliable network connection, but voice traffic tends to be fairly robust in terms of dealing with errors. The errors themselves, as we'll see, can be caused by things like congestion, where data packets are dropped because there is too much traffic on the network. These days, most networks are fairly reliable in that we do not get many errors caused by incorrect connections. So the delays themselves are either fixed or are variable. For fixed delays, we can have things like the processing delay, which is typically fixed. So the voice gets converted into digital form. There's a delay in that processing. Then it gets packetized and serialized. It is then queued by an intermediate devices as it goes through, and then once it is ready to be processed, it's processed, and then there is a propagation delay caused by the delay in the actual transmission. Even though data travels at near to speed of light speeds, it can still take a considerable amount of time in the transmission of the data. Then at the other end, it is then deserialized, depacketized, and then deprocessed to give us our finished voice. The fixed delays are typically the time to propagate. It tends to be fairly fixed, but the time in the queuing, the time in queues can be variable depending on the number of data packets on the network. Also, the time taken to process will also be fairly variable. These elements here tend to be fairly fixed. So it is possible for us to basically calculate or estimate some of these elements, the propagation delay, the processing and packetization with serialization, to give us an idea of the overall cost in time, but the variable can be the queuing and the processing time. Jitter is a parameter, a metric that's important in voice, and basically we don't want too much variation in the delay between the samples being received. Typically it must be less than 20 milliseconds. So for this we typically have things like jitter buffers in our devices which tries to smooth out the delay. So in this case this sample may be delayed by a short time, and this sample may be brought forward so that we get an evening out of the signals. Unfortunately we get jitter overrun, and that's because the buffer, the jitter buffer itself, cannot handle the too many changes in the data transmissions, and this leads to drop packets. We can also get jitter underrun, where the delays are actually too great for it to be able to be smoothed out. There are many different methods which are used to define the quality of service. One technique is to use classification, and with this we typically tag or identify voice traffic from data traffic. Then we can apply technologies such as forwarding, and that's where we can use fast switching of data frames from one network to another. With this, if we can use forwarding rather than routing, then we can have high bandwidth, high throughput networks. We can also have queuing, where we can place different types of data in different queues. Each of these queues can have different priorities, so that we could service one queue over another one. We can also have marking. With marking, we mark the tags with a special code, so that when the intermediate devices read the data packets, they will decide which queue they go into, how fast they deal with it, the data frames, the packets, and so on. We can have policing, and with this we can actually define that different data streams have different bandwidth throughputs, and we can drop data packets which have a lower priority. We can have different scheduling. With different scheduling we can have a round robin queuing system where we go from one data packet queue to another and then back again, or we can have a prioritization where we always take data from the highest priority queue. Then we can have traffic shaping, where we can smooth out the traffic, remove jitter, or reduce excessive bandwidth usage. Along with this, we can actually define which data packets to drop. Typically we might want to drop data packets but allow voice packets to go through. The two key terms that we have in quality service are int-serve and diff-serve. With diff-serve, or differentiated services, the quality service is defined on a hop-by-hop basis. We do not get an end-to-end quality service, and each device will cope with the quality service as the data packet goes through the route. With this, we mark the ToS field in the IP header for the basic priority. The great strength of this method is that it's fairly easy to implement in each of our devices. The weakness, though, is that we've got to tag each packet, and it's only a best effort. With int services or integrated services, we get an end-to-end quality of service. And with this, we typically use a protocol such as RSVP, which will reserve the bandwidth for us and monitor it as we make the connection. Unfortunately, all the devices in the whole route have to be enabled for RSVP. The strength of it is that it gives us a guaranteed quality service, but is not scalable as we've got to enable it on all our devices, and also RSVP actually requires some bandwidth. So the basic process that we have is that we typically define the classification and or the marking of the traffic. We then define the queuing method and the conditioning on the traffic. For classification methods, we can go for policy-based routing, such as route maps. We can prioritize or create queues. We can mark with ACLs or with a protocol or packet size. We can go for committed access rates we can mark these with ACLs, the DSCP tag, quality service groups or rate limit ACLs. And for all methods we can use class maps, as we'll see. The marking option itself can either happen at layer 2 or layer 3. In layer 2 we tag with 1P, and 1P takes the COS field within the Ethernet tagged 1P frame. If the value is a 0, it's best effort, 1 is medium, 2 is high, and so on. There are 3 bits, so there are 8 different levels for 1P. At the IP level, we can mark the ToS field inside the IP header to create our diff serve, and there are 6 bits in here to give 64 different levels. 2 bits are actually used for congestion. For diff serve, we mark the ToS field within the IP header. We have 64 different levels for this, in which 2 bits are used for congestion. So the original specification for the ToS field was this, where we defined a 3-bit precedence value, these ones P0, P1 and P2, to give us 8 different levels. There is now a move away from this towards the new standard, which now uses up 6 bits in the ToS field. These 6 bits are defined as the DSCP headers, and we have another 2 bits for congestion notification. So we have 64 different levels, and these are some of the levels here. So we have 4 different classifications and 3 different drop levels. For this we can have AF11, AF12 and so on to AF43, followed by CS1 to CS7. To define the traffic to match on the device, we define a class map for our IP traffic, and in this case we match the DSCP CP value of AF31. When traffic comes in with these tags, then this will match that value. Once we've tagged or identified the traffic, we can then define the queuing methods. One of the most useful methods is called priority queuing. With priority queuing, we have 4 different levels of queue. Level 1, 2, 3 and 4, or high, medium, normal and low. With this, the data packets that come into queue 1 will always be serviced first. Once those are empty, the system will go on to the second queue. Once that's empty, on to the third queue. If a data packet was to come in for the first queue, it will automatically go back to the first again, and so on. Only when the other 3 queues are empty will it get to queue 4. So it will always empty the highest priority queue first. This is excellent for prioritizing voice traffic, which might be in the high queue, but unfortunately the data traffic can feel starved, especially if there are many higher priority data streams coming in. One way around this is to go for a weighted round robin queue. With this, we can have our priorities defined, but we give the opportunity for the lowest queue to have some opportunity to still be serviced. For class-based, we can automatically determine what traffic should go into what queue based on the classification of it. For weighted fair queue, we can define where the traffic is going and from and where it's going to, and determine the queue for that traffic. And then there is a low latency queue where if the priority is high, it will always be processed first. Otherwise it goes back into the weighted fair queuing. The devices try to cope with congestion as much as possible. For this we have a root processor, and the root processor will continually fill the buffer, either the ingress or the egress buffer, and drop tailing will watch to see when the buffer becomes full, and then try to drop the tail to relieve the buffer so that it can handle incoming data packets. If we have a TCP connection, this can cause the data to be retransmitted, which can actually cause many problems on the network. For voice traffic, because it's UDP based, then there is no retransmission, so there are typically just packets dropped. We can have a random early detect and a weighted random early detect. With this, there is some early detection that the buffer is going to overflow, and then data packets are randomly deleted from it. With a weighted, then there is some priority given to the data packets, so that lower priority ones are dropped first. On the Cisco device, we have what's called a Modular QoS. With this, we typically define a class map to classify the traffic, then define how the traffic is policed, and eventually we apply the policy. So in this case, we have a simple ACL to match the traffic that we find interesting. Anything from this network will be defined in this case. This should be 101 to match this value here. So we define a class map, class 1, and in this case we say match access group 101, which will match this. Anything with this address is matched with this class map. Then we define our policy map. So in this case, we apply the policy to this class, and we say that we have a certain bandwidth, we have a queue limit of 30 data packets, and in this case we're going to set the DSCP value in those data packets to AF112. So this allows us to mark the data packets as they come in. After this, we apply the policy onto an interface, in this case on E0 on the outgoing, E1 on the outgoing direction. Okay, so here's another example. Again, we use an access list to actually define the traffic. So in this case, anything going from that network might be one voice network to another network. In this case, it's this network, and we've defined that as access list 108. We define our class map, and in this case, we match to this ACL. So this defines our class map. Next, we define our policy map, and we apply our class map into this and define the bandwidth. We can see we can do other things such as police and set quality service values. Then we define a queue limit, in this case of 21. So we define the policy map. Then finally we apply the policy map onto an interface, in this case the outgoing direction of FA01. The different queuing methods that we have are priority queuing. With priority queuing, we can set a queue limit for each of our 4 queues. So this defines the limit for our low queue, our normal queue, our medium queue, and for our high queue. And then we can apply this priority list onto our interface, in this case onto the serial 0 port. And we can see here an example. We have high limit, medium limit, high limit, medium, normal, and low. We can also have priorities for certain protocols, ranging from IP, HTTP, and so on, IPX. So in this case, we define that HTTP has high priority and IPX has low priority for the protocols. For custom queue, we define a custom queue list, and in this case we can actually define the queue limits for each of the queues. So in this case, IP packets will have a queue limit of 40, where CDP is only 20, and we apply it on here. Custom queuing can use up to 16 queues in a round-robin manner. Example of custom queue configuration: we create our queue list, in this case number 1, and then we can define different protocols. In this case we could go for ARP or CDP, IP, IPv6, and so on for our protocol. Then we can define up to 16 different queues from 0 to 16, and after that we can actually define which, if we want to classify any other packets with an ACL. We can also do it on TCP. So in this case we could classify for IP and TCP, and then we can classify the queue for the different TCP protocols such as Telnet or HTTP. So we can see here that we've prioritized Q1 for the web traffic, HTTP. We can also define the limits for the queue. We can see we can get up to 32,767 different queue entries, and also define the byte queue for the size of it. We apply it onto an interface or a VLAN with custom queue list and list number. For weighted for WRRQ, we can actually define the priorities for each of the 4 queues. In this case, we define for Q1, Q2, Q3 and Q4 the values of 3, 8, 10 and 12. Then if we do the calculations, the value for Q1 will be 3 divided by this value, which gives 9% approximately. Q2 will have a value of 8 divided by this value to give us 24. Q3 will have a value of 10 divided by the total to give us 30, and Q4 will be 12 divided by this value to give us 36.4. So we can see here that this will be the highest priority queue and this will be the lowest one. We take the total, and then to find the percentage we take that value and divide it by the total. So this shows us setting the queue. So we can set for various DSCP mapping values. We can also define the limits at which the queue starts to drop the data packets. Another protocol which is used in networks to monitor the traffic is the span protocol. For this, we can say that we monitor the source. In this case, we monitor interfaces 1 to 2 for the traffic that they receive, and we send all the received traffic to this port here. So we could have an intrusion detection system here listening to the data packets. Span allows us to send the data from these 2 ports to that host. With remote span, we can actually send the data to another switch or another device. In this case, we set up a VLAN, define a remote span, define the ports that we want to save and we want to capture, and we define that it's saved to a remote VLAN 10, and then we can save to that interface.